Hello, am I audible?
Yes, sir.
Okay, so good morning to all. So today we
Morning,
have
sir. Good morning, sir.
okay. So in the last class we have discussed about the surface line integral, surface integral, and volume integral. Okay. So today we will be studying the application of these particular uh, integrals. Okay. So first of all, we will see the divergence of a vector. Now, divergence of a vector is the operation with the use of del operator. Now, till now we have seen that del operator has been applied on a scalar. Okay, suppose v was a scalar and we used to call it the gradient of v, gradient of the scalar v. Okay, now when the scalar we applied a gradient on it, so we used to get a vector. So this was a vector. Okay, that we know that when del operator is applied on a scalar, that del operation can be only be applied as a gradient form. So we call it a gradient of a scalar, and the result is a vector. Yes, someone is still entering. Let me admit them. Okay. Okay. Now this is known to us. Okay. Now we have also seen that now we will be actually studying the del operation on vectors. Now before starting the del operator, we have seen that del operator is nothing but it is a derivative operator which is applied on 3-dimension or 3-coordinate system. Okay, 3-dimensional coordinate system. So del operator is nothing but it is a derivative operation which is applied on 3-dimensional coordinate system. So when del operator is applied on a scalar, we call it a gradient of a scalar, then scalar becomes a vector. Now the del operator can be applied on vectors also, but there are two possible ways of applying the del operator on a vector. So since we know that del operator itself is a vector, and when you are applying it on another vector, so that means we know that there are two possible ways where we can operate two vectors at a time. Suppose vector A and B, what we can do, we can either apply dot product or we can apply cross product. Here also in del operator, we will apply the dot product between del operator and the vector, that is called the divergence of the vector, and the del operator can be applied on a vector by cross product. So del operator cross vector is called the curl of a vector. So there are two operations, one is divergence and one is curl. Divergence means del operator dot vector, and curl is del operator it is actually in the next slide. Okay, so the del operator cross vector. Okay, so there are two possible ways. Now obviously when we apply del operator dot vector, that is the divergence of a vector, the resultant will be a scalar quantity. Why? Because dot product results in a scalar quantity. Okay, so result is a scalar. Now what is divergence? So divergence, we know that we are doing del operator dot vector. Okay, so what is actually significance? Why we are doing this? It is not like that we are just ऐसे मन किया कि del operator vector उसको सर dot product करते हैं, उसका नाम देते हैं divergence, और एक cross product करते हैं, उसका नाम देते हैं curl. ऐसा नहीं है. There is some specific reason why the dot product is done and why the divergence name has come into existence. That is also based on that specific reason. So okay, so now till now for gradient we have seen that gradient of a scalar means that whenever we are shifting from one particular scalar quantity v1 into another scalar quantity v2, if we choose the shortest path, then we calculate the derivative of that scalar, change in scalar, that is v2 minus v1, that is dv, divided by dl, that is distance between the root, okay, or that is displacement. Okay, so that is now the maximum rate space rate of increase, now maximum space rate of increase, okay, of a scalar is obtained. Okay, maximum space rate of increase then it is called the gradient of that scalar. Okay. Now what is divergence? Divergence means the divergence of A, that is a vector A, at a given point. At a given point is the outward flux per unit volume as the volume swings about P. So suppose we consider a sphere, okay, three-dimensional circle, that is a sphere. Now within the sphere there are flux, okay. Okay. Now the fluxes are coming out of that particular sphere. Suppose inside there is some electric charge, okay, and fluxes are coming out like this. So fluxes are coming out. So when fluxes are coming out of the particular means sphere, okay, now it is told that it is what amount of fluxes are coming out per unit volume, means amount of flux coming out per unit volume, okay. It is called the divergence of that particular vector. That means vector is actually suppose if you consider in this way, suppose the fluxes are coming out is phi, okay, fluxes are coming out is phi. Now as we have discussed in the previous lecture that we generally don't calculate the total flux like this, okay, we cannot measure. So what we do, we use a unit surface, okay, surface area of 1 unit meter square like this, okay. So this one surface and the surface area is ds, okay. So now if the total flux is phi, psi, then the amount of flux which is coming out from this surface is d phi or d psi, because total psi is 100%, so amount of flux coming out from this surface is, say suppose 10% of psi, okay, so it is d psi. So the formula is, if we calculate that in this way, d psi divided by ds, so what we get? We get the flux density, suppose A, okay. Generally in electric flux we write B, or actually magnetic flux we write B, and in electric flux we write D, capital D. But in this case, since we are using this A vector, so suppose this vector is A. Now if you want to find out the total flux, what is the total flux? That will be integration of psi, okay. Now integration of psi means, from this equation number 1 we can write d psi equals to A dot ds, because A is a vector, ds is also a vector, but flux is a scalar quantity, so it will be dot product, okay, it will be a dot product. Now coming to this equation, now total flux will be integration of d psi, so it will be integration of A dot ds as per this equation, okay, replacing this value over here with this, okay. Now since this integration is with respect to surface, so we call it a surface integral. Now in our case, the surface integral, it is actually a sphere, okay. Surface integral is actually a sphere, okay, it is a sphere. So sphere means it is having a volume. So in the last class we have seen that a closed surface integral is actually said to be a volume, okay. So that means this is a volume, so we call it as closed surface integral, क्योंकि ये volume a sphere है, तो इसके लिए closed surface integral, because surface is closed. So this is the total amount of flux coming out from this particular surface. Now what is the amount of flux coming out per unit volume? Because this area was for flux density, because the amount of flux coming out from this area is flux density and total flux is psi. Now flux per unit volume, that will be this particular equation divided by volume, isn't it? Total flux per unit volume, that is we are talking about psi divided by volume, Okay, that is equals to surface integral of A dot ds by volume. Now it is told that the divergence of a vector A at any point P is the outward flux per unit volume as the volume shrinks about P. That means there is a point P over here. Point P. So the fluxes are coming out from this sphere. But suppose we assume that this sphere is shrinking. Shrinking means ये छोटा हो रहा है. Previously the sphere was like this. Okay. Now suppose we draw another sphere where this particular sphere has become a smaller one. Suppose very small. Okay. And point P is here. And the fluxes are coming out. Now fluxes are remaining same. Flux का जो magnitude है वो change नहीं हो रहा है. वो अभी भी psi है. ठीक है. Psi. SI it is told. So the flux is psi. But the point P, the volume is shrinking as if it is becoming a point. और देखते देखते ये सिंपल एक पॉइंट बन जाएगा. एक सिंपल पॉइंट बन जाएगा P. वॉल्यूम जो है वो श्रिंक होता जा रहा है और फ्लक्स जो है वो बाहर निकल रहा है पॉइंट से. ओके. फ्लक्स सेम है. तो if this situation occurs, okay, that means the amount of flux which is coming out per unit volume, okay, that means it is a measure of the outward flux per unit volume as the volume shrinks about P. That is a point. That means the flux coming out per unit volume from a sphere, but sphere is shrinking to a particular point. देखते देखते छोटा होता जा रहा है. ऐसे सेकेंड स्टेज में ऐसा छोटा हो गया. फिर then at the last it is becoming a point. So it is nothing but the total flux coming out per unit volume when the volume is nothing but a point, shrinking about a point P. That is called the divergence. Divergence, why the name divergence is given? Divergence name is given because it is see from this point the fluxes are diverging, coming out. Okay. Now there is a opposite of divergence which is called convergence. That is P, and if the fluxes are entering, then it is called convergence. We call it negative divergence. Okay. So this is positive divergence. Okay. And this is negative divergence. Okay. So this is the statement. So divergence of A, that is del dot A, is equals to the flux per unit volume. So this is flux per unit volume, no doubt. This one, this is flux per unit volume, total flux. Okay. Per unit volume, but volume shrinks about P. So that means volume is shrinking. So volume tends to 0, limit tends to 0. So this is called divergence. So if it is asked what is divergence, divergence is nothing but the surface integral. Divergence of a vector is nothing but the surface integral of a vector, closed surface integral of that vector per unit volume when the volume is shrinking to a particular point. Okay. So is it understood? Have you understood the definition of divergence?
Yes, sir.
Okay. Someone is still entering. Let me admit them. Okay, so this was all about the divergence definition. Now see, in figure 3, as I was telling, that it shows that figure A, suppose 3A, shows the divergence of a vector at a point P is positive because the vector diverges or spreads out at P. So it is called positive divergence because it is diverging out. Figure 3B is a vector has negative divergence or convergence. So this is also divergence but negative. And figure C has zero divergence. Suppose there is a point and vectors are traveling. So we call that P is not having any divergence, zero divergence. But suppose in this case, if you see that there is a point P and vectors are coming out, we call it a positive divergence. And if it is converging, we call it a negative divergence. Okay. So this is called a source. This is called a sink. Okay. And this is neither a source, neither a sink, this point. So just the definition, okay, you can say over here. and how it is calculated, that is not required because this question doesn't come. This is for your reference only, these previous slides. Now let us concentrate on this particular this 13 equation. So how to write the divergence of a vector? Divergence of a vector is quite easy because in del operator, that means in gradient, we have seen that del operator is represented in Cartesian coordinate system like this. Okay, del y unit vector y plus del z unit vector z. We have seen this. So when we used to calculate divergence of a gradient of a scalar, suppose scalar is x, so we used to put x over here. So what used to happen? This entire thing used to become a vector. Okay. Now in our case, in this divergence case, it is little bit different because in this case, the divergence which we are having, okay, that is divergence of A now, which means it is actually the dot product of two different vectors. So vector number 1 is del operator, that is del x unit vector x plus del y unit vector y plus del z unit vector z. This we know. But since it is A is a vector, so what we will do? We will have a vector also vector, so it is having a vector coordinate. So ax unit vector x plus ay unit vector y plus az unit vector z. Now if you perform the dot product, so what we will get? We will get this dot this. So del x ax plus del y ay. This is just a dot product, simple, which you have already studied in mathematics in schools. Okay. So dot product between two vectors. तो ये अल्टीमेटली क्या है? ये स्केलर है, क्योंकि इसका कोई डायरेक्शन नहीं है, कोई यूनिट वेक्टर नहीं है यहाँ पे. There is no unit vector. So it is a scalar quantity. That is why you can see the divergence of a vector in Cartesian coordinate system. It is a scalar quantity. Okay. Now for a cylindrical coordinate system, just use the del operator in cylindrical coordinate system and take the a vector in cylindrical also. You do the dot product, you will get this result. Okay, this can be done, and this is for the spherical coordinate system, same thing. Okay. Now let us come to a theorem which is based on this divergence of a vector, which is called the divergence theorem. A divergence theorem tells us that as far this theorem is concerned, it is told that it can be used for transforming any surface integral to a volume integral. That means transforming a closed surface integral to a volume integral. So divergence theorem states that the total outward flux of a vector field A, actually it is spelling mistake, this field A through the closed surface S is the same as the volume integral of the divergence of A. That means if you take this closed surface integral of a vector, that is equals to the volume integral of the divergence of a vector. Okay. So if you have this volume integral of a divergence of a vector, you can transform it to a closed surface integral of that vector. Or if you have the closed surface integral of a vector, you can convert into the volume integral of divergence of the vector. Okay, so now let us see the proof of this particular theorem. So it is told that suppose if you concentrate on this figure 5, okay, figure 5. So it is a volume, okay. So it is a volume, and this is a suppose a closed surface. Okay, this is a closed surface. So closed surface obviously it is having a volume. So volume is V, which is equals to the closed surface integral of S. Okay. Now we already know this. Now let us see how we can apply on a vector. Now subdivide the volume V into large number of cells. Okay, if the kth cell has a volume delta Vk and it is bounded by the surface Sk, that means this particular volume is divided into small segments. Okay, small segments. Okay, small segments it is divided, and each segment is having an area of delta Sk. Okay, delta Sk is the area. Now if you concentrate on the left hand side of this equation, LHS. Okay, LHS is this. Now what we will do, we have divided the entire area into small segments. Okay, that means this particular area is divided into small segments. So S, capital S is equals to, either we can write ds, but this is delta S. So what we will do, suppose it is divided into k number of cells, okay, or suppose n number of cells, it is divided into n number of cells, suppose 1 million, okay, n number of cells is divided. So what we will do, we will do a summation, k equals to 1 up to n delta Sk. That means अगर n नंबर ऑफ सेल्स है तो हर एक सेल का एरिया है डेल्टा S, तो डेल्टा S1 प्लस डेल्टा S2 डॉट डॉट डेल्टा Sn तक ऐड करेंगे तो टोटल S हमको मिलेगा. नाउ यूजिंग दिस कॉन्सेप्ट, इफ यू हैव द क्लोज सरफेस इंटीग्रल, okay, closed surface integral of a vector, so that means if you separate that particular, if you separate this particular vector from this surface area, तो क्या लिख सकते हैं? We can write that it is the surface integral, all right, okay, but it is with respect to the delta Sk, where summation is from k1 to n. Okay, summation is from k1 to n. So it is delta Sk, actually it is Sk. Okay, delta S or delta Sk, dot delta Sk, we can write also ds, same thing, we could write ds over here. Either you write delta Sk over here or over here, anywhere. Okay, okay, so that means this total area, surface area, is divided into segments. Okay, so that means the total S is now summation of delta S. So total integral, if I see this equation, the total integral, surface integral, is nothing but small integrals. That means इसका मतलब है कि वेक्टर जो है, वेक्टर के साथ पूरा A का, A वेक्टर के साथ पूरा सरफेस का इंटीग्रेशन नहीं करेंगे. ये जो है इसके अंदर वेक्टर है, वेक्टर A, इसके साथ इंटीग्रेट करेंगे, इसके साथ करेंगे, इसके साथ करेंगे, तो सबके साथ करने इंटीग्रेशन करने के बाद फिर इसका एडिशन होगा. So that means we are integrating the vector, surface integral of the vector with the each and every small cells. Then we are adding the total number of cells to get the total surface integral. Okay, now we are using this, so this is equals to this. Now we will, what we will do, we will multiply delta Vk on numerator and denominator. What is delta Vk? Delta Vk is nothing but, since V is the total volume, so this total volume is divided into small segments. Okay, so that means मतलब के मान लो, if I draw a cuboid, okay, total cuboid है, तो एक cuboid का 3-dimensional cuboid, so it is having some surface area over here, it is having some surface area over here. So suppose this surface area is S. Okay, this surface area is S and the total volume is V. Okay, so एक cube का कितना surface है? How many surfaces are there in a cube or a cuboid? Hello?
6.
6. So 6 surfaces. So S is one of the surface. Okay, S is one of the surfaces. Suppose it is a cube. All the surfaces are of equal dimension. Equal means you can say measurement. So front is S. अभी इसको हम छोटा छोटा हिस्से में अगर बांट देंगे, मान लो कि छोटा सा क्यूब हम यहाँ से टुकड़ा निकालते हैं, ठीक है, तो छोटा टुकड़ा टुकड़ा जो होगा उसका वॉल्यूम होगा डेल्टा वी। ओके, अभी उसका जो टुकड़ा है, उसका जो फ्रंट का सरफेस है, दैट फ्रंट सरफेस इज हैविंग द एरिया ऑफ डेल्टा एस, isn't it? So that means similarly here also the total volume is there. We have divided into small cells. So each cell is having some area and also some volume. Okay, so delta S is the cell area of the small cell where the total area is S and the total volume is V. So that cell which you are taking, it is three dimensional, so it is having a volume of delta V. Okay, volume of delta V. So that delta V, क्योंकि एक एक टुकड़े को लिया है हमने, तो एक एक टुकड़े को हम इंटीग्रेशन करेंगे फिर समेशन करेंगे। तो वो पहला टुकड़ा जो है kth, मतलब कि kth सेल है, the kth cell, so we are integrating with respect to kth cell and we are taking that volume of that kth cell. Okay, then we are dividing in the numerator and denominator. Now since we are doing that, this part we have seen somewhere where it is nothing but the divergence. It is the divergence of A as per this particular equation. Okay, as per this equation is divergence of A. So that means we can write similarly. So this is divergence of A. So यहाँ पर क्या लिख सकते हैं हम? Next step क्या होगा? Divergence of A delta Vk. Now we also know that in statistics we use summation. But if it is a continuous summation, then we can transform into a integration also. Same thing. Integration is also the summation but continuous form. So we will write this as volume integral of divergence of A. Got it? So that is why a surface integral, closed surface integral, is divided into small segments, where each segment is having some small area and volume. We will divide that volume in numerator and denominator. We will convert it into divergence, okay, equation and divergence form, and then do this volume integral and convert this summation into volume integral, and we get the volume integral. So this is the divergence theorem. Okay, understood? Have you understood this part?
Yes, sir.
Okay. So let us see some numericals. Okay, and this numerical is quite easy. There is not too much difficulty because there are three questions are given. That means three part. The same question is same, that we have to calculate the divergence of the vector, but over here the vector p is given in the Cartesian coordinate system, vector q is in cylindrical coordinate system, and vector t is in spherical coordinate system. So as per this equation which we have seen, equation number 13 is for Cartesian, 14 is for cylindrical, and 15 is for spherical. We will just use them and calculate the divergence of that particular scalar vector. Okay, this is just the mathematical portion, so I am skipping this part. So now let us move forward to the curl of a vector. A curl of a vector, it is also the operation, that is another operation that we know, that we have already talked about, that is the cross product of a del operator and a vector. That means cross product of a del operator and a vector is called curl of a vector. So what is the definition of curl of a vector? Curl means it is actually a rotating vector, a vector which is rotating. Okay, so a curl of A, that means curl of a vector A, is an axial or rotational vector whose magnitude is maximum circulation of A per unit area as the area tends to 0. It tends to 0. Let me correct it. Okay, so as the area tends to 0, that means it is the maximum circulation of A per unit area as the area tends to 0, whose direction is normal of the area when the area is oriented so as to make the circulation maximum. Now, curl of a vector is nothing but the cross product of del operator and the vector. Obviously, if you perform the cross product, the resultant will be a vector. Okay, so that means till now we have studied about 3 operations of del operator. Number 1 is del operator on a scalar, which is called gradient. Resultant is a vector. Then number 2 and 3 are the del operators on vectors. So first one is dot product, that is the divergence, you get a scalar, and second one is the cross product, that is the curl, and you get a vector. So this, in this case, the curl of a vector, you will get a output as a vector. So it is nothing but a rotating vector. Suppose a vector is rotating, okay, and circulating around a particular area or a point. So the amount of maximum circulations of A per unit area, that means at a particular point, if you are having the maximum circulation of A, okay, maximum circulation of the vector A per unit area, okay, where the area tends to 0. In this case, the area tends to 0. So that is called the curl of the vector. That means in this case, suppose there is a vector like this, so it is rotating or circulating. It is circulating. Suppose it is circulating this way. It is circulating. The vector is circulating. In the clockwise direction. Okay. Now, the amount of circulations, okay, it is the magnitude, whose magnitude, that means the curl of a vector whose magnitude is maximum circulations of area. So that means the maximum number of circulations of A per unit area as the area tends to 0. That means suppose there is an area like this, okay, there is an area like this, surface area, okay. So we have to measure how many circulations are there per unit area. So it is nothing, so it is the maximum circulation of A, that means circulation of the vector A per unit area as the area tends to 0. That means the area is shrinking. In this case, the area is shrinking. So area was previously like this. Now the area has become very, very small. Suppose the area has become very small like this, tends to 0. So still we are getting the maximum circulation. Okay. So that is called the curl of the vector. Okay. Now the resultant. Now if this is the magnitude of that particular curl of a vector, okay, that is the maximum circulation per unit area when the area tends to 0. Now what will be the resultant? Now we know surface. If you are taking a surface, the surface is a vector. Now surface unit vector is always perpendicular to its, perpendicular to the surface, okay, on which it is lying. So whose direction is normal direction of the area when the area is oriented so as to make the circulation maximum. So direction will be normal. Okay, so the resultant will be normal, or you can say not this way. It will be the opposite way, other way around. It will be like this. The direction will be normal. So the equation is same thing. The curl, that means the total. In this case, we call it the total closed line integral. Why total line integral? Because if I concentrate on this, if I represent in this way, if I redraw it for you, that means there is a vector. A vector, it is circulating. If I draw a thin line, that will be easier. The vector A is circulating. Now the total length, it is a contour. Okay, so the total length is L. Now if you take a small segment over here, if you take a small segment, this is DL. Okay, we know that integration of dl will give you total L. Okay. So what is the line integral actually? Line integral will be closed line integral because it is a closed line integral. Closed line. So it is closed line integral of A dot dl. Okay. Now if you are putting a vector over, a particular area over here, if you are putting an area to measure the amount of circulations, okay, to measure the amount of circulation which is there, we can see. So that area is S, delta S, as if the delta S is almost a point. Okay, because this line, it is a line, so it is almost a point. So what is the maximum circulation per unit area? Okay, maximum circulation per unit area, that is simple, divided by delta S. So circulations per unit area means circulation is nothing but the line integral of the vector, because vector is rotating. It is rotating means it is actually traveling in a closed line. So vector, we have to calculate the closed line integral, simple. So we will get the circulation, maximum circulation per unit area. So if you put a area over here, it is tends to 0, so you will get the per unit area, and resultant will be perpendicular. So it is told that where delta S is bounded by curve L, okay, and an is the unit vector normal to the surface. That means this is the unit vector. Okay. This is called the curl of a vector. So this mathematical proof is not required. Okay, this is what. So now let us concentrate on the calculation part, which is more important for your exams. So representation of the curl. Now, similar to divergence, where we have seen the divergence was a dot product. Dot product. So we have taken del operator dot vector. But in curl, since it is cross product, so you will take the del operator क्रॉस प्रोडक्ट विद दी वेक्टर. तो मान लो डेल ऑपरेटर का क्या है, डेल ऑपरेटर जैसे हमको पता है कि ये है डेल डेल एक्स यूनिट वेक्टर एक्स, ठीक है. इफ आई टॉक अबाउट द कार्टेशियन कोऑर्डिनेट सिस्टम, ओके, और वेक्टर क्या है, वेक्टर है ए एक्स यूनिट वेक्टर एक्स प्लस ए वाई यूनिट वेक्टर वाई प्लस ए जेड यूनिट वेक्टर जेड. तो क्रॉस प्रोडक्ट कैसे करते हैं? Very simple. You take the unit vectors. Okay, ax, ay, az. That means unit vector x, unit vector y, unit vector z. Okay, तो ये सेपरेट कर लिया हम लोगों ने, इसको बैठा दिया जैसे क्रॉस प्रोडक्ट होता है, ठीक है. और जो कोएफिशिएंट होता है वो कोएफिशिएंट को एक एक करके लेंगे. यहाँ पर ले लिया, फिर ये वाला कोएफिशिएंट और ये वाला कोएफिशिएंट. सिंपल, वी आर डूइंग द क्रॉस प्रोडक्ट एज जस्ट लाइक मैथमेटिक्स. So we will get this particular vector. Same for cylindrical coordinate system and similarly for spherical coordinate system. Okay. Now talking about the another theorem which is called the Stokes theorem. Okay, I am covering this part because since you have understood divergence theorem, then the Stokes theorem is also quite easy to understand. So Stokes theorem is used for transforming a surface integral to a line integral, or a line integral closed line integral to a surface integral. Here what we are doing, we are converting the closed line integral of vector A equals to, it is equals to the surface integral of curl of A. Just like in divergence we have seen that closed surface integral of vector A is equals to the volume integral of divergence of A. Over here we can see the closed line integral of A is equals to the surface integral of curl of A. Okay. Now, how to prove this? How it is coming into existence? Suppose same thing. What we will do? Previously, we have taken in divergence theorem. We have considered that there was a volume, and we have divided that entire volume into small cells, where each cell is having some surface area of delta S, and the volume is delta V. Here, what we will do? We will take a contour. Okay, of some surface, but it is not a closed surface, it is an open surface. So closed path and open surface. So if you take an open surface, obviously there is a closed path, okay, and the total surface area is capital S, and the total length of the closed path outside boundary is capital L. Okay. Now if you take small segments, that means here also the total area is divided into small segments. Okay, we are dividing it into small segments. So each segment is having some length delta L, okay, and area is delta S or ds, whatever. So same thing we will do over here. So rather we are converting this particular figure in like this. Okay, if you see this particular figure, this is the same thing. Okay, here we are concentrating or zooming in on this particular part, okay, where the entire surface is divided into small cells. Now, each cell is having a length. Okay, now displacement is a vector, so it is having some directions. Now over here, if you see, it is circulating in the anticlockwise direction, suppose. So suppose it is circulating in the anticlockwise direction. Okay, so what will happen in this case? It is going right and then upwards. If you consider the right one, if you see, it is going left and downwards. So here they are cancelling. So in this intermediate sections, they are cancelling each other, and the total vector is the line vector. Okay. So if the cells are having their own length del dl, okay, if you take the closed line integral, so closed line integral means line integral of this part plus line integral of the second part, second cell. Okay, that means line integral of the first cell, line integral of the second cell, line integral of the third cell or fourth cell. Okay. Okay, so line integral of the fifth cell, sixth cell, and so on. So that means line integral of this segment plus this segment. So what we are doing, we are converting this total line integral, closed line integral, into the closed line integral of individual cells, first cell, second cell. Then we can convert into the summation. So same thing. See, procedure, if you can remember divergence theorem, the way we have proceeded, we are doing the same thing. We are moving in the same direction or same way. Okay. So in this case, what we will do, we will now divide and multiply delta S on numerator and denominator. What is delta S? Delta S is nothing but the surface integral, surface area of this particular cell. क्योंकि dl क्या है? dl means this line on length. Okay, length of cell 1, length of cell 2, length of cell 3, that we are doing. But this length is also having some area, surface area. So we are taking the surface area. So each individually, this is one particular cell. Suppose this is one cell, cell number 1. ये cell number 1 का length है, ये length है, और ये area है. उस area के साथ divide कर रहे हैं और multiply कर रहे हैं. Then k equals to 2, k equals to 3, and so on. Now if you concentrate on this particular part, this is nothing but because delta sk is just tends to 0, it is tends to 0. So we can use this particular equation. This equals to curl of A. Okay, that means the ratio of the closed line integral of A divided by area, where area tends to 0. Here also we are doing the same thing. The ratio of closed line integral of A divided by area, where area tends to 0, because it is divided into small areas, very small, tiny. So this is nothing but the curl of A. So what we get? We get summation of curl of A delta sk. Delta sk means this one, this delta sk, delta s1, delta s2, delta s3, एरिया जो है हर एक सेल का एरिया. Now we similarly in previously what we have seen that summation can be converted into integration, है ना, summation can be converted into integration that we have seen. 2 minutes. Wait. Okay, so we have seen that we can convert a particular summation into a integration. So here also what we will do, we are converting this summation, okay, this summation into integration. So this is the summation, so we are converting into an integration. What integration? Surface integration, because it is a surface integral. Okay, so hence we can prove that the closed line integral of any vector can be transformed into the surface integral of curl of that vector, okay, by using this procedure. Okay. So have you understood this part, Stokes theorem? Okay, so these two theorems are actually very similar to each other, divergence and Stokes. So divergence theorem is applied by using the divergence of a vector, and Stokes theorem is applied using the curl of a vector. Okay. Okay, so I will upload these lectures in the YouTube. Okay, and I also very soon, once I get the permission, I will also share the notes with you. Okay. Okay, so first tell me, did you get any notes